For a second I was in control. I had it once, I lost it though. And all along the fire below would rise. And I wish you could have let me know what's really going on below. I've lost you now, you let me go. But one last time, tell me you love me.
Technical position is okay. We can pass even meteorological conditions. What do you think?
I think they sound like really good conditions.
So we're going to go for lunch on the original schedule. That also means that in about 1 hour the bone rangers need to assemble.
Remember once upon a time that I was yours and you were blind. The fire would sparkle in your eyes and mine. So tell me you love me. If you don't, then lie. Oh, lie to me. Just tell me you love me. If you don't, then lie. Oh, lie to me. If you don't, then lie. Oh, lie to me. Call it true, call it true love. Call it true, call it true.
12, 10, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Lift off, lift off.
What do you do when your record-breaking rocket, 2 years in the making, disintegrates only 20 seconds into flight? Good afternoon. My name is Owen, and this year I have the privilege of being the team manager of Stratos IV. In this video, I would like to proudly present to you the design of the Stratos IV vehicle. A design not only spanning the last 5 months, but the full 10 years since the launch of Stratos I. The story of the Stratos project is the story of a student team's quest to reach space, the area 100 kilometers above the Earth's surface, where there are freezing temperatures, no atmosphere, and bombarded by radiation. So, why do we set the most inhospitable environment known to man as our destination? There's a couple of reasons. First and foremost, space is the final frontier. As Carl Sagan eloquently describes it, in space, the open road softly calls to humanity. Herman Melville, in Moby Dick, captures it even more poetically, saying, "I am tormented with an everlasting itch for things remote. I love to sail forbidden seas." Sailing the forbidden sea of space is a childhood dream of many, and the Stratos IV team has not forgotten this dream. Beyond this, many DARE teams work late into the night, and these nights are the perfect opportunity to look up into the sky and see the moon hanging above you. It's a hugely motivating factor to know that the technology you work on a daily basis helped put men on that moon 50 years ago. And it's a pretty strong motivating factor when it doesn't go away and hangs in the sky right above your head. Beyond its mystical appeal, space is absolutely ripe with opportunity. Since the dawn of the space age, when it was seen as a domain for military conquest, space has slowly shifted to an area of science, with 2018 showing the highest number of objects launched into orbit than ever before, 157 of these being CubeSats, satellites you can fit in the palm of your hands. The applications and resources presented in space are being recognized at an ever-increasing rate. This so-called new space demands increased innovation, shorter project timelines, and smaller rockets. The Stratos project hits all three of these, giving students hands-on experience with real-life rocket science. And lastly, we want to democratize space. The term rocket science is a synonym for the complex. Space is seen as this far-off, intangible place that is of little use to us. Through our quest to reach it, we want to raise awareness of what space is, how rocket science works, and how maybe it's not so hard, and how space plays an essential role in our everyday lives. With this as our goal, what have we done to reach it so far? Delft Aerospace Rocket Engineering, or DARE, was founded in 2001, with the aim of giving aerospace engineering students the opportunity to get some hands-on experience with rocket science. Since then, we've grown to become a society of more than 180 active members, coming from a host of different faculties here at the TU Delft, and working on nearly every different aspect of modern rocket technology. The Stratos project takes all of these different aspects of technology and puts them together into one rocket, and then we launch these boundary-breaking vehicles. To this end, we started with Stratos 1. Stratos 1 was a two-stage solid rocket, and it launched from the Esrange Space Center in Sweden in 2009. With Stratos 1, we set the European amateur rocketry altitude record at 12.5 kilometers, a pretty respectable start on our path to space. After Stratos 1, we went back to the drawing board and developed Stratos 2, a single-stage hybrid rocket. After an unsuccessful launch attempt in 2014, the modified Stratos 2 Plus returned to the Sedea launch site in Spain in 2015. Stratos 2 Plus also carried with it an onboard camera, giving us our first glimpse of our destination. Stratos 2 reached an apogee of 21.5 kilometers, and with this apogee, we broke the record we'd previously set with Stratos 1. However, since then, the high-end team from Stuttgart set a new European amateur rocketry altitude record at 32.3 kilometers, and so the Germans took the lead in the race for space. After Stratos 2, the Stratos 3 project began. Stratos 3 built upon many of the technologies used in Stratos 2, as well as developing a number of new systems required for the higher altitudes that we were aiming for. Stratos 3 returned to the Sedea launch site in Spain last summer with the goal of reclaiming the European amateur rocketry altitude record. Stratos 3 took 2 years to design, build and launch. It involved the development of an entirely new engine, more powerful than ever before and requiring 15 full-scale tests to fine-tune. It required the development of brand new composite lightweight structures, the new methods of deploying recovery systems while returning at supersonic speeds, and the complex electronics required to control all of these different processes. However, as we saw at the start of this video, the Stratos III flight did not go as planned. 20 seconds after liftoff, at an altitude of approximately 10 kilometers, going 3 times the speed of sound, Stratos III disintegrated. The team returned to Delft and an investigation was begun. The investigation team consisted of members of the Stratos III team who had an intimate knowledge of the vehicle, as well as new members of the Stratos IV team who brought a fresh perspective to the investigation. As we use a telemetry system on the vehicle to stream back all of the information being gathered from pressure sensors, inertial measurement units, and the GPS, we were able to piece together quite a complete picture of what happened to the Stratos III during its flight. In addition to this data, we also had the data gathered from ground systems, such as the radar and Doppler measurements. This allows us to say with quite a degree of certainty that we have pinpointed the root cause of Stratos III's demise. This root cause is a phenomenon known as roll-pitch coupling. This occurs when the roll motion of the vehicle, how quickly it likes to roll around its longitudinal axis, matches in frequency the natural pitch frequency of the vehicle, how much it likes to move its nose up and down during the flight. When these two frequencies match each other, the vehicle becomes unstable and diverges from its nominal path, and this divergence causes it to break up. This phenomena can be caused by a number of different root causes. Some of these include the length over diameter ratio of the vehicle, the stiffness of the whole vehicle as well as each of the interfaces, as well as the roll and pitch frequencies the vehicle likes to move at. Now, in this animation, constructed using the data gathered from onboard IMUs, you can see that rather than moving in a linear fashion, the vehicle cones around a certain point, and then when these two frequencies I spoke about match, the vehicle flips over, becoming unstable and breaking up. So, what do you do when your record-breaking rocket, 2 years in the making, disintegrates only 20 seconds into flight? I'm not sure about you, but in DARE we strive to push ourselves forward to even higher, more ambitious goals, which is why this year, with Stratos IV, we have set our sights on the finish line to this student space race, 100 kilometers. Now, you're probably thinking, 20 kilometers to 100 kilometers, that's a bit of an ambitious leap. And you'd be right, it most certainly is. But there's a number of reasons we are confident in taking this leap. Firstly, there's the potential of the vehicle. So towards the end of Stratos III's development, we saw that the performance of the motor we had produced, in combination with the mass of the vehicle we had produced, meant that the predicted apogees coming out of the simulations were coming close to 100 kilometers. We weren't quite reaching it, but we were starting to get close. Secondly, with the concluded investigation to Stratos III, we're quite sure that we've pinpointed the cause of the disintegration, meaning this year we can actively work towards mitigating this phenomenon. And lastly, this year we have a bigger team than ever before, with 15 full-time engineers and 60 part-time engineers working to bring this project to completion. So, with space as our goal, let's take a look at how difficult it really is and how high our goal really is. Let's start with something a bit tangible, the Eiffel Tower, standing exactly 300 meters tall. If we zoom out a small bit, we come up to 10 kilometers. This is the cruising altitude of a commercial airliner. Here you can fit 33 Eiffel Towers beneath you. Zooming out once more, we get to 30 kilometers. Here, 98.5% of the Earth's atmosphere sits below you. Only 4 aircraft have ever reached altitudes above this. Zooming out one more time brings us to more than 3 times this height at 100 kilometers. That's 333 Eiffel Towers. Here, the entire Earth's atmosphere sits below you. In the sun, the temperature is plus 120 degrees Celsius, and in the shade, minus 100. A human will lose consciousness in these conditions in less than 15 seconds. So, you can only imagine, from this height, the view is pretty nice. Here, if you were to sit 100 kilometers above Delft, if you look to the west, you'd be able to see beyond the west coast of Ireland, to the north, up to Oslo, Helsinki and Copenhagen, to the east, all the way past Warsaw, and to the south, all the way down to Monaco and Milan. That's 2,200 kilometers from horizon to horizon. So, you could only imagine getting this high is no small feat. Well, that's our destination for this year. How are we going to get there? Ladies and gentlemen, without much further ado, I give you the design of the Stratos IV vehicle.
As Owen mentioned, we want to show that rocket science is not that hard at all. But as you saw from the video, it's not quite that easy either. I'm Krijn, the systems engineer of the project, responsible for the final design, and I would like to take you through the design of Stratos IV in a bit more detail. But before I do that, I would like to refresh your knowledge on rocket science a bit. The first question we have to ask is, why do you actually need a rocket to go to space? Can't you just fly an aircraft a bit higher? But as Owen said already, at 30 kilometers, 98.5% of the Earth's atmosphere is already below you, which means that there is no oxygen for combustion that has to happen in the engine. There are two more things other than oxygen that you need for combustion, which are heat and fuel. And a rocket engine has a lot of both. The difference between a rocket and an aircraft is that the rocket takes its own oxygen, so you don't need the oxygen from the air for combustion. Now the only thing we need to do with this combustion is create a force to push you up into the air. And we can create this force by throwing out a lot of gas from the exhaust of the rocket. And just like when you let an inflated balloon go, the rocket will move into the opposite direction. And it turns out that to create the highest force, we need to get as much fuel and oxidizer as possible and burn it as fast and as hot as possible. Now big companies like SpaceX do this by using very complex engines using liquid oxygen and liquid kerosene. But these engines can easily take more than 10 years to develop, and the budget runs into the hundreds of millions. And since we don't have 10 years and we have a budget that's lower than the total amount that NASA spends on coffee every year, we need to compromise. And this is why we use a hybrid rocket engine. This engine uses a liquid oxidizer and a solid fuel. but at the cost of efficiency. Even though this engine is supposed to be less complex, it has been in development for over 3 years. And this is why we've decided for Stratos IV to use a similar engine as the Stratos III. But if we don't have an engine with more performance than before, how do we then make sure that we go higher than ever before? Well, as I'm sure you all remember from high school physics, our friend Newton told us that the acceleration of the rocket is proportional to the force that we create divided by its mass. And so there are two things that you can do to create a very high acceleration, which are create a very big force or have a very small mass. And as I told you, since we don't have a bigger force each year produced by the engine, we have decided for Stratos IV to focus completely on minimizing the mass of the rocket. So now that you know everything about rockets again, I will take you through the design of Stratos IV. The Stratos IV rocket consists of several sections. The flight starts with a phase powered by the engine. This engine produces an insane 26 kilonewtons of thrust, which is enough to lift a proper size SUV straight into the air. It also creates 31,000 horsepower, which is more than 40 Formula 1 cars combined. The engine is controlled by the engine bay, which guides the flow of oxidizer from the tank section to the engine. And we've introduced a new section this year, the roll control section. And as mentioned before by Owen, this section is entirely designed to mitigate the risk of the roll pitch coupling motion. And there's two things that you can do to mitigate this motion, which are spin the rocket very fast or don't spin the rocket at all. And we've decided to not spin the rocket at all. And the roll control section needs to ensure this. At Apogee, we split the rocket into two parts. And we discard the tank and the engine section because we won't need it after this point anymore. But we do recover the recovery bay section, which allows us to safely land the rocket, or the nose cone section, and the nose cone section itself, which houses all of the flight electronics that control all the systems in the rocket. So we can zoom in a little bit on this nose cone. And we can see that we've designed the nose tip to be made out of 3D printed steel. And we do this because it turns out that when you're flying 5 times the speed of sound through the atmosphere, that the friction with the air actually becomes so bad that the tip of the rocket heats up to more than 300 degrees. And this is way too much for the shell that is made out of Twaron, a material similar to Kevlar, to handle. But by using this Twaron material over the glass fiber that was used before, we save 2 kilograms on the nose cone shell alone, while it is still transparent to all the signals that are transmitted by the telemetry antennas that are on the inside. These telemetry antennas transmit everything from the data about the position of the rocket, the velocity, the payload, the pressure sensors, but also video footage that we record during the flight. If we zoom in a bit more, we can see the flight computer, the brain of the rocket. This flight computer consists of 7 custom designed PCBs that control everything in the rocket from parachute deployment to the storage of all the flight data. Below the flight computer, we've implemented a battery management system, which is basically a fancy word for a rocket charger. This system allows us to charge the batteries while they're still inside the rocket, whereas before we had to always take them out to charge them. We also implement 2 black boxes, which will store all the data during flights so we can recover it when we pick up the nose cone from the sea. Also, 2 static pressure sensors are included that measure the atmospheric pressure during the flight, which will make sure that we can determine the altitude that the rocket has reached. So these sensors are very important for determining if we've reached space, but also to determine at what altitude the parachutes should deploy. Then, if we move down a section, we move to the recovery bay. And this recovery bay makes sure that we can safely land the nose cone after separation. We've completely redesigned the recovery plate, which is the plate that holds all the forces from the parachute deployment. This plate is so strong that you could hang a fully loaded Mitsubishi Outlander from it and it wouldn't break. We've also introduced a heat shield, because it turns out that when you're falling from 100 kilometers, atmospheric heating could actually damage the sensitive parachute wires that are stored underneath it. We use a dual parachute system with a drogue parachute and a main parachute. And the drogue parachute will slow us down when the nose cone is falling at 2 times the speed of sound to a velocity where we can open the main parachute. And this will then slow us down even further to the safe landing velocity of approximately 50 kilometers per hour. We implement 5 cameras with 3 radio cameras looking straight out from the body of the rocket, 1 camera looking down the body of the rocket, and 1 camera looking straight through the recovery plate and the heat shield, such that it can capture the moment of separation as well as the moment of parachute deployment. And as I said, these cameras will, or the footage of these cameras will be transmitted live through the telemetry antennas to the ground, such that everyone can see the moment that we reach space. Now we move to the section that is new this year, the roll control section. And at the top you can see the separation system. This uses a steel clamp band that will shoot off when actuated, and then springs will be used to push the 2 parts of the rocket apart. We've added an umbilical connector that connects the rocket to the ground in this section. And the reason for this is that we have a lot of new systems in this section that all require power. And the way we used to do it was that we would run all the power cables from the umbilical connector in the engine bay, then run them all the way along the tank up to the nose cone. But since we require so much more power, this would actually become way too heavy. So this is again a weight-saving measure. We also have a dip tube that sticks into the tank to make sure that we cannot fill the tank with too much oxidizer. And then on to the roll control system, the system that this section was introduced for. And it consists of control electronics as well as a thruster system. And we use 4 thrusters to control the roll rate of the rocket during flight. So basically we are flying 5 rocket engines this year instead of 1. The roll controller is a newly designed piece of electronics that has to make sure that we keep the roll rate of the rocket within bounds. It uses gyroscopes to measure the roll rate of the rocket and will then send a signal to the thrusters, which will then have to correct if the roll rate is too high. You can also see the thruster valves. They allow flow from the main oxidizer tank to the small thrusters. And we can zoom in a bit on these thrusters. Here you see 2 out of the 4 that we have. They're made out of 3D printed steel. And as I said, they use the nitrous oxide from the main tank, which is then run through a catalyst bed of nickel oxide, which will create a chemical reaction that creates gas. And this gas will then create the thrust similar to the way that the main engine creates thrust. Then on to the tank. The tank was of such complex design that we have decided for Stratos IV that we would take the Stratos IV tank and use exactly the same design. It is still made out of a thin aluminum liner, which is then overwrapped with carbon fiber to hold the insane forces that are induced by the 60 bar nitrous oxide that is stored within it. If we move down, we can see the engine bay. And a traditional problem in there and with many rockets that we've built is the alignment and the structural rigidity of the rocket. By using conical interfaces, with the bolts angled upwards, we make sure that we can properly align all the sections within the rocket with the benefit of adding structural rigidity as well. The center of the engine bay houses the feed system. We use a baffle to make sure that the oxidizer does not swirl in the supply line, just like what happens when you pull the plug out of your bathtub. We use an ignition valve to allow for a small flow of oxidizer from the tank to the engine to start the engine. And we have a tank pressure sensor to monitor the pressure in the tank during filling operations, which makes sure that we cannot have it getting too high pressure in the tank, and which could cause dangerous situations. Finally, we have the main valve, which allows for the full flow of 6 kilograms per second of oxidizer from the tank to the engine. And then, of course, the engine bay also houses a lot of electronics. You can see the engine control unit that controls all the valves and motors that are in this section. And then we get to one of the most, and maybe the most important system in the entire rocket, which is the flight termination system. And in this case, the flight termination receiver. When the rocket flies out of the predetermined safe to fly zone, this system will trigger and will then break up the rocket into two parts, such that the rocket cannot fly outside of a predefined safety boundary. Because if that would happen, it could potentially hurt people or cause damage to property. So this system entirely ensures that we can safely launch our rocket. We still have the umbilical connector in this section that I talked about before to supply power to all of the systems inside the engine bay. The final systems in the engine bay are the fill valve, which will be used to fill the rocket up with all of this propellant, and the flight termination antennas, which will pick up the signal from the ground when the flight termination system needs to be triggered. And then we move down to the final section, the engine. And I said before that we would use the same engine as Stratos III, but this is not entirely true. While we've kept the inside of the engine completely the same, we've completely redesigned its outside. To have better stability of the rocket, which is one of the means of mitigating the roll-pitch coupling motion, we have bigger fins, and they are now over 1 meter in height. We also implement a composite combustion chamber. And by using this over the aluminum combustion chamber that we used before, we save a massive 6 kilograms on the combustion chamber. And this combustion chamber is made out of several layers. We have a carbon fiber layer on the inside that has to hold all the pressure forces of the engine at the heat of the combustion gases. Then we have a foam core that will bridge the gap between the smaller diameter of the engine and the larger diameter of the tank, such that we have a rocket with the same diameter everywhere. And finally, we have a thin layer of carbon fiber again, which adds stiffness to the entire engine. Then we get to the last part. This is the part that we've saved the most mass on any part in the rocket. This is a titanium nozzle. Before we used a full graphite nozzle, which was very heavy, but in this design we still use two small pieces of graphite, which will take the majority of the heat of the engine. But at the parts where the gas flow is cooler, we can use a titanium shell, which will also then be used to mount nozzle to the engine. And the nozzle is used to make sure that the gases are pushed out of the engine as fast as possible to create the highest force. So that was a really quick walkthrough of the design of Stratos IV. And now Owen will tell you a bit more about what will happen from this phase until the launch.
Thank you, Krijn. So, designing the rocket is probably the easy part. Now we get to the production, testing, and probably inevitable redesign of certain parts. As the lovely renders show, we now have a finalized design for Stratos IV, and production is well underway. As we speak, the tanks that make up the bulk of the vehicle are being wrapped in Belgium. The titanium nozzles that will be used in the next few engine tests are being coated in Switzerland, and new parts are being churned out of the Dream Hall here in Delft every single day. Once all of these parts are produced, they have to be tested. One of the downsides of rocketry is that we can't take our rocket for a test lap around the track. We get one shot at launching it, so our launch is our test. This means that every single component, system, and subsystem that we can test is tested. Once everything has passed all of these stringent checks, the sections that Krijn spoke about will be integrated, and in May, an 8.5 meter long rocket will emerge from the Dream Hall. Then we will pack up the rocket and ship it off to the launch site. The launch campaign is the pinnacle of the entire project. However, it is not the moment for the team to relax. If anything, things get even busier. Firstly, we have to unpack everything from being shipped, check it for damage, clean it, set up an assembly area as well as offices, and then slowly all of the different sections will be reassembled and tested. We then have to ensure that all of our equipment, as well as the vehicle, can communicate with all of the infrastructure that's based at the launch site. In addition, we stay in close communication with the launch site personnel for the entire duration of the campaign. Unfortunately, we can't launch rockets from wherever we'd like. This means that we have to launch them from areas where we can control the sea, land, and airspace where the vehicle may enter during the course of its flight. Therefore, during the full launch campaign, we have regular meetings with launch site personnel to exchange up-to-date information about our latest simulations as well as the conditions surrounding the planned moment of launch itself. As I mentioned, we only get one shot at launching the rocket. Therefore, we rehearse every single step that we can to ensure that the launch goes as smoothly as possible. This means that we practice moving the rocket to the launch tower, putting it into the launch tower, raising the launch tower, filling the rocket with the nitrous oxide that it needs to launch, and then communicating with the vehicle right up until the moment that it is ready to take off. Last but not least is the launch procedures themselves. The Stratos team occupies all of the key positions during these procedures. The control room oversees all of the different operations to be carried out during the launch operations. The bunker communicates with the vehicle as well as the payloads on board. And lastly, the telemetry stations receive the telemetry down from the vehicle during all the different stages of the flight to ensure that we have all of the information as well as live video feed streamed back from the rocket. When all of the procedures have been gone through seamlessly, the clock reaches 0, the main valve opens, 6 kilograms per second of nitrous oxide flow into the combustion chamber, and Stratos IV will rise skyward on a pillar of flames. Now, this launch site, as I mentioned, is of importance. Historically, Stratos missions have launched from the Esrange Space Center in northern Sweden and the Sedea launch site in southern Spain. However, this year, as Stratos IV is aiming to go higher than ever before, we also need an area larger than ever before to accommodate the flight, which is why this year we are planning to launch from the Denel Overberg test range in South Africa, meaning this is the view that we should have in the downward facing camera as the upper capsule of Stratos IV separates from the lower tank stage in August of this year. Everything is on track for this design to grace the skies of South Africa this summer. Krijn and I have had the pleasure of presenting this design to you. However, It took 70 student engineers working long days and late nights for over 5 months to complete this design, so they all deserve recognition for their tireless work. As I also mentioned, we stand on the shoulders of those who've come before us. We would not have a design this advanced or complex without the well-laid foundations by previous Stratos teams and their members. And lastly, I would like to sincerely thank all of our partners for supplying us with material, advice, tools, machining, and finances. Without all of these contributions from every single one of them, we would not be able to bring this project to its completion. Thank you very much for your attention, and I look forward to presenting the rollout of the Stratos IV vehicle to all of you in about 3 months before we pack up the vehicle, ship it off to South Africa, and send Stratos IV to the stars.